Let's use partial fractions to integrate x squared plus x plus 1 divided by x plus 1 quantity squared times x plus 2 dx. The first thing we need to do is make sure our denominator has a higher degree than our numerator. And in this case, our denominator is factored for us already, but if we multiplied it out, we'd see that it was a third degree polynomial, which means it is of higher degree than our numerator. The next thing we do is factor our numerator and see if anything here can cancel. But in this case, our numerator is as factored as it can be. So we can just get right to using partial fractions. So taking a look at our denominator, we see that we have case 2, which means that our denominator contains repeated linear factors, because x plus 1 is linear and it has multiplicity 2. We also have a distinct linear factor of x plus 2. So when we rewrite this integral, we need to create a term for every power of our repeated factor up until the power we were given, plus a term for our distinct linear factor. So that will give us some constant a divided by x plus 1 to the 1 plus some constant b divided by x plus 1 squared, which is the power we were given, plus some constant c divided by x plus 2. We can use this information to create an equation to solve for a, b, and c, because if these two integrals are equal, then their integrands are also equal. So that will give us x squared plus x plus 1 divided by x plus 1 quantity squared times x plus 2 equals a divided by x plus 1 plus b divided by x plus 1 quantity squared plus c divided by x plus 2. And we can simplify this by multiplying both sides by this denominator. So multiplying the left side by this denominator just gives us the numerator, which is x squared plus x plus 1. Multiplying this fraction by this denominator will cancel one of our x plus 1's, giving us a times x plus 1 times x plus 2. Multiplying this fraction by this denominator will cancel both of our x plus 1's, giving us b times x plus 2. And then multiplying this fraction by this denominator will cancel our x plus 2, giving us c times x plus 1 squared. We can use this equation to choose values for x that allow us to cancel some of our constants so we can solve for others. So for example, both of these groups have an x plus 1 in them, but this middle group does not. So if we choose x equals negative 1, then this becomes negative 1 plus 1, which equals 0, canceling out a. And the same thing happens over here, canceling out c, leaving us with just b to solve for. So let's try that. If x equals negative 1, then on the left we have negative 1 squared minus 1 plus 1. And on the right we have 0 plus b times negative 1 plus 2 plus 0. And now we can just solve for b, giving us b equals 1. And we can substitute this back into our equation. That will give us x squared plus x plus 1 is equal to a times x plus 1 times x plus 2 plus 1 times x plus 2 plus c times x plus 1 squared. And now we just have a and c to solve for. And we notice that both groups contain x plus 1, but only this group contains x plus 2. So if we'd like to isolate c, we can choose x equals negative 2, giving us negative 2 plus 2 equals 0, canceling out a, and leaving only c to solve for. So let's try that. If x equals negative 2, then on the left we have negative 2 squared minus 2 plus 1 equals 0 plus 0, because this is another negative 2 plus 2, plus c times negative 2 plus 1 squared. And we can just solve for c. And that will give us c equals 3. And we can substitute this back into our equation. So that will give us x squared plus x plus 1 equals a times x plus 1 times x plus 2 plus x plus 2 plus 3 times x plus 1 squared. And now we just have a to solve for, and the easiest way we could solve for a is just choosing x equals 0. So if x equals 0, the left side becomes 1, the right side becomes 2a plus 2 plus 3. And then solving for a, we get a equals -2. Let's substitute these values back into our integral. That will give us the integral of -2 divided by x plus 1 plus 1 divided by x plus 1 squared plus 3 divided by x plus 2 dx. And this can be written as a sum of integrals, giving us the integral of -2 divided by x plus 1 dx plus the integral of 1 divided by x plus 1 squared dx plus the integral of 3 divided by x plus 2 dx. And each of these can be integrated using u substitution. So for the first integral, u equals x plus 1, and that will give us -2 ln absolute value of x plus 1. For the second integral, u equals x plus 1, giving us -1 divided by x plus 1. And for the third integral, u equals x plus 2, giving us 3 ln absolute value of x plus 2. And now we just add plus c for our constant of integration.